Good evening, everyone. My name is George Kraw. My wife, Raphael, and I are sponsoring this series of lectures to just help demonstrate the wonderful and important science that's being done in Santa Cruz. And tonight we have an especially wonderful story, I think a uniquely Santa Cruz story. This is Ryan, the story that Ryan will share with us tonight is about a combination of young, accomplished professors working with a group of even younger, non-traditional students, applying creative approaches to efficiently use tools distributed around the globe, leading up to a scientific discovery of a spectacular nature, something that could only happen here at Santa Cruz. Ryan is a highly regarded scientist. He's currently a Packard, Sloan, and Kavli Fellow, organizations that have invested in his work because it shows such promise. In the short time he's been with UC Santa Cruz, he arrived in 2016, he's already had a tremendous impact on the campus. And I just want to say, it makes me so proud when I see what we have done, what the school has done over these years, and especially the discovery that Ryan will be discussing tonight, how this can come about from the university that I went to. So Ryan, please.
Thank you all. Thank you very much. This is fantastic being here. I don't get across the hill enough. It's great to see people. This is a great opportunity. And so tonight I'm going to tell you quite the tale. And I was told specifically that I needed to make things flashy. And in science, the flashiest things you can have are Einstein and gold. So hopefully that got you in the door, and then I can wow you with some science. I don't think I have any equations, but there will be a quiz. Okay, so I just wanted to let you know, scientists or at least people interested in things like science have been searching for gold for hundreds of years. This is the area of alchemy, and this actually pushed science forward for a long while. Now, I, as a scientist, and in particular an astronomer, my goal was not actually to figure out how to make gold, even though we ended up doing that. Really, what I'm in search for is discovery. And for anybody who's truly discovered something unique and new about the universe, it is the most amazing feeling you will ever have. And what I'm showing you here is exactly that. What you see in this message between a graduate student, a postdoc, and myself is exactly that moment of discovery. And we'll get back to that, but first I need to introduce the players. So here is a subset of our team at UC Santa Cruz that's been working on gravitational waves and trying to figure out what the light is coming from them. And so, I'll go through a handful of these people, but before you get caught up with the names and the individuals, it's very important to note that everybody except for myself and the guy standing next to me, Enrico Ramirez Ruiz, who's also a professor and in fact the chair of the astronomy department, everybody else is either a graduate student or a postdoc in our group. This is an incredibly young group. And you'll also notice that it's an incredibly diverse group, where more than half of the people in this group are either female or from an underrepresented group. And that mirrors both our department generically. We are a relatively diverse department where roughly half of our graduate students are female, a large fraction of them are underrepresented minorities, and the campus as a whole, and of course the population of California. And this is part of what we strive to do, is to get that diverse population into the ranks of science, because they come at these problems from dramatically different perspectives. And so I'll point out a couple of people that we'll come back to in particular. So in particular, there's Charlie Kilpatrick all the way on the edge here. He's a postdoc on our team. He'll be one of the people who's looking at some of the data in real time when we get to that part of the story. And then in particular, I'll point out the guy in the middle here, Dave Coulter, who's a graduate student, and he comes from a non-traditional background. He actually has a history degree. he did what all history degree holders do for a few years. He tended bar and odd jobs. And eventually decided that that's not how he wanted to live his life. So he taught himself how to program, went back to school, did night school, and then left a 6-figure programming job to go to graduate school. And this is the sort of person who other programs might just look past. Somebody with a history degree, who is this guy? And we welcomed him with open arms. And because of that background, that was really one of the key reasons why we were able to make this discovery. Okay, so we'll come back to these guys in a little bit. But first, I wanted to start off with something pretty fundamental, and that's that you, in your body, you are made of atoms. And in fact, your body is composed of about 10 to the 27 atoms. So that's a 1 with 27 zeros behind it. It's a huge number of atoms. It's so many atoms that there are more atoms in your body than there are stars in the observable universe. So that should tell you how many atoms there are. And one of the things that you probably don't think about on a daily basis, I don't even think about on a daily basis, but I think about a lot, is where did those atoms come from? So when you think about your body, by mass, most of us is oxygen. Of course, we know that most of a person is made out of water, H2O, and that oxygen is heavier than the hydrogen. So oxygen makes up more than half of the atoms in your body. After that is carbon, and then hydrogen, and then nitrogen. Those are the main components of our body. So I wanted to focus in on that most important component, oxygen. So oxygen is an interesting atom because it was not around when the universe was formed. When the universe was formed in the Big Bang, you primarily just had hydrogen and helium, the 2 lightest atoms on the periodic table. And there was no oxygen. So how did we get oxygen, which is a relatively light element? It's pretty basic for human life. Where did that come from? Well, it turns out that you get oxygen from stars. And here, stars, a massive star, something that would enrich the universe with oxygen. This particular one would have maybe 10 to the 58 atoms. So that's much more than the human body. That's a 1 with 58 zeros behind it. I don't even know what that is. That's not quite a Google, which I'm sure if there are Google employees know exactly what that is. So what ends up happening is that in these furnaces at the centers of massive stars, you're converting light elements into heavier elements. You turn hydrogen into helium. You turn helium into carbon and oxygen. And you keep going up and up and up until eventually you produce, at the center of that star, a core that's made of primarily iron. And iron is the most bound atom that you can have in the periodic table. And so if you continue to make it heavier, it actually takes energy to do that. So a star doesn't want to do that. It doesn't want to give energy into making heavier and heavier things. So eventually what ends up happening is that core becomes so massive, it's unstable to its own gravity, and it collapses down. When it does that, when it collapses down at the very center, when that happens, it happens almost instantaneously in a few milliseconds. And that will create a shock wave that propagates outward throughout the entire star, and the outer layers of the star get ejected out into the galaxy. And that means that all those other elements that were created in the star, including all the oxygen, they get flung out into space. And this is a real image of what we call a supernova remnant, what happens after that star explodes. This is a real image primarily focusing on the oxygen. Most of the material that you're seeing here is oxygen. And so over time, this oxygen gets mixed in with that primordial gas that was made in the Big Bang. And together, you end up getting the kinds of things that can eventually coalesce down and make planets and make us. Now, oxygen is an incredibly robust atom. Atoms in general are very robust. And what that means is that the oxygen that is in your body now really is the same oxygen that was formed in those stars. And so when you've heard that phrase that we are all made of stardust, that's what that means, is that we really are made from these components of stars, that the oxygen, that the nitrogen, the carbon that is in your body was originally formed in the centers of these massive stars. Now, that means that, this oxygen has been around, that's in your body, has been around for billions of years. And if you think about how oxygen cycles in and out of the atmosphere, what ends up happening is that at any point of those 10 to the 27 atoms that you have, about 1 billion of them, that's a small fraction of 10 to the 27, that about 1 billion atoms you share with every other person at some point in your life that you shared with them in their life. And that doesn't just go for every living person. So you can look to the person next to you, in front of you, behind you, and you've shared about 1 billion oxygen atoms with that person. But it also is that we've shared those billion atoms with every other person who's ever lived. So that includes people like Cesar Chavez or Frida Kahlo or William Shakespeare. And so some of that inspiration, hopefully, also is imprinted. And we can take that form of shared humanity and think about how we really are all together in this in one way. Now, in those 10 to the 27 atoms that you have in your body, a very small fraction, 10 to the 18 or so atoms, are gold. Gold doesn't really do much for humans. You don't need much of it in your body. A lot of it is just there because it's around in the environment. But we actually have a higher percentage of gold in our bodies than, say, you would just find in water. If you just take a bucket of seawater, there's some gold in there. It's not as much as what you have. Now, there's just not that much gold around in the world to begin with. It's a very rare element. And in fact, if you take all of the gold that has ever been mined by civilization, it tallies up to about 165,000 tons, which means that you can make roughly 10 Google buses made out of gold. Which is not that much, right? That's not that much. And so you should say, all right, so you don't have to do much to get all the Earth's gold. But of course, the Earth is just one place. Most of the mass in our solar system is in the sun. So how much gold is in the sun? It's a tiny amount. Up there in the corner, what I've shown is the equivalent of a small asteroid. This is actually the biggest asteroid that we have, Ceres, but it's tiny compared to, say, the Earth or the Moon. So Ceres down here in the corner is much smaller than the Earth or the Moon. But if you just took the mass of Ceres and you turned that into gold, that's roughly the amount of gold that's in the sun. And you can see however many trillions of dollars that it would be equivalent to. Of course, if you mined all that gold from the sun and then you dropped it on the market today, it would destroy the market. It wouldn't really be worth that much. I don't have an economics degree, so don't trust that much. So we know that gold's around. We know that we can make this a lot of the heavier elements like oxygen in stars, but gold is actually something that's harder to make because gold is heavier than iron. So normal stars cannot produce gold. So I'll give you the recipe for making gold. This is true alchemy here. So first, you need lots and lots of neutrons. So maybe you remember this back from your chemistry or physics classes. Heavy elements have a disproportionate number of neutrons relative to protons. That's not the only reason why you need these neutrons, but just consider that you definitely need a lot of neutrons. So that's your ingredient. Then you need to compress to incredibly high densities, much larger than the center of the sun, much larger than the centers of massive stars, much larger than a lot of the things that we've ever encountered in our lives. And then heat to about 1 billion degrees, roughly. And then you'll do this. I didn't set the timer, but you need to do it for about 2 milliseconds, and you'll generate a bunch of gold. And so what I've described here is actually there's an easy way to do this. All you have to do is, if you need a lot of neutrons, maybe you've heard of a neutron star, you take 2 of those neutron stars and then you ram them into each other. And in doing that, you create that high density, high temperature environment. And when that happens, you can produce gold. So for people who don't know what a neutron star is, we'll just start with the size. So a neutron star is roughly the size of a city. So here, for comparison, is the size of a neutron star relative to San Francisco or San Jose. And you can see they're roughly about the same size. You could imagine even just thinking of the San Francisco skyline and seeing the curvature of the neutron star above it. But they have the mass of more than the sun. They're more massive than the sun, the size of a city. That means that they're incredibly, incredibly dense. And what we want to do, this is actually kind of the system that I was showing before, where in that movie, where these two neutron stars are, a few times their size away from each other. And what we want to do is, drag them together and have them go bang. Now, the density of neutron stars are so high that you can take a bucket of neutron star material, and that's roughly the same mass as Mount Everest. Okay. Another way to think about this, I find this to actually be the better one, but another way to think about it is if you take a sugar cube of neutron star material, that's more mass than all of humanity combined. Okay. So that's one of the key components. Now, I already said I need to shove two of these neutron stars into each other. How likely can that be? Right? You don't see two stars in our solar system. How often does this happen? Well, it turns out that about 2% of all neutron stars are in binary systems, and in close binary systems where there's the potential for them to merge. But there's this tricky thing about when you have two objects orbiting. Just like the Earth orbits the sun, we're not crashing into the sun. So what you need to do is actually take away some energy from the orbits of those two neutron stars to cause them to come closer and closer together. And what I'm showing here, in addition to the neutron stars spinning around each other, is these ripples that are coming outward. Those are gravitational waves. So, we should be asking ourselves, what are those? We'll do that in a second, but just keep in mind that they're kind of critical to this whole scenario, that they're taking away the energy from the system and bringing those two neutron stars together. So what are gravitational waves? Let's maybe take a step back and just think about waves more generically. Coming from Santa Cruz, of course, I'm very familiar with this kind of wave. And then, this is something that's common throughout all of our interactions. You just might not realize it except when you see it on the water. So here's a movie of two layers of the atmosphere that are producing these waves, and you can see it because of the clouds there. So this is the same thing. There are waves all around. Whenever you have fluids interacting with each other, you generally produce some waves. Another kind of wave that we interact all the time, you're interacting with it right now, is light. Light is produced as a wave. And in fact, this is the way that we observe is using optical light, but there's a range of wavelengths and energies to light. And so you could go from X-rays or even beyond X-rays, the highest energy photons we would call gamma rays, and then all the way down to radio. And so this entire spectrum of light, all of that are also waves. And so really what light is a way of transporting energy, right? So anybody who has solar cells on their roof, they know this, right? The light shines on those solar cells, you generate energy. And the same way, if you've ever had an infrared heat lamp, or even just your oven glows, if you look at charcoal that's hot, you'll see it glowing. That's light, that's radiation that you're seeing, the photons are coming off, and that's transporting that energy, that heat. So this is just a way of transporting energy is through these waves, light. And about 100 years ago, Albert Einstein came across this interesting idea of really kind of going one step beyond what we had thought about for gravity. And a consequence of that is a way that we can transport energy beyond light. So what Einstein thought of was that gravity is not this idea of just an apple falling to the earth like Newton's thought of. It's really this idea that gravity, that mass and space and time are all intimately linked, and that there's a way of describing the universe in terms of this space-time that gravity can adjust through mass. So if you have a massive object, you've probably seen diagrams like this before. If you have a massive object like the sun, it can distort space-time from your nice flat grid and make it so that there's this ripple in it. And then if you have a less massive object like the Earth, it'll have a smaller dent in that sheet of space-time. And this is a new way of thinking about gravity, instead of this idea of just attractive forces, is really exactly this quote by John Wheeler, that matter is telling space-time how to curve. It's telling you, if you have more matter, then it curves more. And space-time tells matter how to move. So now, instead of things just sort of falling into each other, really what's happening is you can describe the orbit of the Earth around the sun as just moving through this space-time along the simplest path. So if you go a few steps further, Einstein came up with a couple of interesting predictions. So one of which is just black holes, that you should have objects that are so dense that even light cannot escape from them. Another interesting prediction from this is that gravity can bend light, because it's changing space-time. What we perceive as straight lines are not the simplest lines in that curved space. And so this idea is important, where you can have light coming towards the sun and then bent around to the Earth. And what you would see, you would think that the star is further away than where it really is. That bending of light is critical. And we can zoom in on this. So this was one of the great predictions of Einstein, saying that space-time is real and that light was affected by this change in the space-time, even though photons have no mass themselves. So this was predicted in 1916, and then a year later, there was a way to check this. So normally, this is a very hard experiment to do, because if you notice, you're trying to see a very faint star past the sun, which is incredibly bright. And usually when you look towards the sun, don't look at the sun. But if you were to look at the sun, you wouldn't see any stars nearby because the sun is so bright. Except in one instance, which is when, of course, the moon is in front of the sun. And so there was an eclipse, about a year later, where Arthur Eddington, this famous astronomer from England, was able to make measurements of these stars when the moon was blocking out the sun. And this is just a comparison of where those stars were before and after, if you have the sun in front of it or not. And you can see pretty clearly that you have doubled stars everywhere. And what that means is this is the star when the sun's not there, and then this is the star when the sun is there. And there are a couple of things that are notable. One is that the positions moved, right? The stars moved. And the other one is that if you're closer to the sun, especially if you look at, like, say, this pair of stars that get doubled over, the motion is larger than if you look at things that are further away. And that's because if you go closer to the sun, you're bent more. You're going further into the gravitational field of the sun, and so you have more bending. And when this was first reported, the New York Times said, "Lights all askew in the heavens. Einstein theory triumphs." It turns out Einstein's right a lot. Back then it was news, not so much anymore. And then here's the real thing: stars not where they seemed or were calculated to be, but nobody need worry. Now this has since been seen in dramatic fashion in something like this. This is called an Einstein ring, where you have a galaxy behind another galaxy, and that light is bent around the galaxy in a way where you see it distorted in this ring fashion around that galaxy. So this is an indication that space-time is real, that general relativity works. And so now we can get back to this idea of what are gravitational waves. So really what we're talking about is, if space-time is telling you how light should move, telling you where mass is, how mass should move around, what happens if you actually take something like the sun and you just shove it over to the side? You move it. You're changing what space-time is doing. And when you do that, you have to tell everything else, all the other stars, all the planets, everything, that you just move this thing. How do you do that? You do that through gravitational waves. So gravitational waves, when you accelerate a mass, it produces a gravitational wave, and these are ripples in the fabric of space-time. And those ripples, they move outward from the system at the speed of light, and they carry with it energy. And that's why when you have neutron stars, these giant, massive things that are incredibly dense, moving around each other, when they do that, because they're moving around, they're accelerating, and they're producing gravitational waves that's taking away energy, and so they have to come closer together. So when these gravitational waves are coming through us, there are plenty of gravitational waves right now coming towards you. In fact, if I were to just do jumping jacks, I would be producing gravitational waves, and they would be distorting your space-time right around you locally. They would be stretching you in different directions. And in fact, you're being stretched by these all the time. It's just at an incredibly small level that you cannot notice normally. And so there was an instrument designed called LIGO, the Laser Interferometry Gravitational Observatory, that was designed specifically to measure these slight changes in the stretching of space-time. So the way we do this is we start off with a laser, right? So if you ever have a physics problem you want to have a solution, you say laser. That's the first step, at least. And the basic idea is, here's the setup: is you have a laser, which I'll turn on in a minute. You have a beam splitter, so it splits the light into two paths. Half the light goes down one arm of what we call an interferometer, and the other half of the light goes down the other arm. So you have these two arms, an L-shaped machine. Each one of them for LIGO is 4 kilometers long, a couple of miles. And in doing that, then the light eventually will come back. These are mirrors at the end. And then they'll come back together, and then they'll be shining on this screen. And if they're exactly the same length, because of the wavelength of light, if they're exactly the same length, then you can produce it so that those little wavelengths either constructively interfere and you get a stronger signal, or if you change things a little bit, they destructively interfere and you see nothing. All the light cancels itself out. So why don't we run through this? So we split the light, it goes down and comes back. And then depending on the length, the relative length of those arms, you either get a strong signal or no signal. So we'll zoom in a little bit, looking at the actual wavelengths of the light. So again, these are the wavelengths of what the light you have. And so in the same way that when you listen to music and you have two speakers and you can hear that beating, sometimes you get positive interference, sometimes negative interference. If they cancel each other out, if they cancel each other out perfectly, we'll have to rerun this. If they cancel each other out perfectly, then you hear nothing. So you can have these nulls, these dead points, when you listen to music in some other scenarios, in particular in this particular scenario. And so because of that, what you want to do is see small changes in those wavelengths, and then that can produce large amplitudes in the amount of light that you see. So here they're coming together, destructively interfering. And if we look on the screen, when this comes together, all right, so first we need to move things. You can already see the beam path is either brighter or weaker. And then we move to the screen, and you can either see the source being stronger or fading away. And so most of the time you actually have very little light, and then if a gravitational wave comes through, then you see these strong bits coming through. And then as those gravitational waves come, because there's a wave pattern to them, you have not just one hit that comes across, you have a bunch of waves that just wash over your instrumentation. So you see exactly that pattern of things getting brighter, fainter, brighter, fainter. And so this is what is actually measured. Now, LIGO has two separate detectors. One's in Louisiana, one's in Washington. And the reason they do that is because you can have a lot of false positives. You can shake the instrument in a lot of different ways. They're actually very seismically stable, but there are a lot of things like just a truck driving by that can cause a fake signal. But it's unlikely that two trucks will be driving by in the same way in both Louisiana and in Washington State. So this is what they end up doing. So this is a complicated plot, so just stay with me. On the bottom here, I'm just showing time for both detectors. And then what we measure is something called strain. And all that is the amount of distance that you can see change divided by the total distance that you have. So this is 10 to the minus 21. You have 4 kilometers long. So you saw something that was 10 to the minus 21 times 4 kilometers big. How big is that? That's about 1/1000th the size of the proton. Okay? So it's an incredibly sensitive instrument. Now, we can see exactly some pattern here that's going through, right? You see these sort of ups and downs in what you're measuring, and those ups and downs both get closer together and they get stronger with time. And that's exactly what we would expect from two massive objects that are orbiting each other, because that orbit sets this up and down pattern. So you have up and down as the two objects are swinging around each other. And then if you're having a stronger measurement, what that is just you're getting closer together, because then you're producing more gravitational waves. And then, of course, what happens is because they come closer and closer together, these peaks, the frequency is going up, which means that you start off orbiting slowly, and then as you come closer together, you're orbiting faster. So what actually was seen here in this first detection, this was the first detection of a gravitational wave source back in 2015. What we saw here were two relatively massive black holes, not neutron stars, black holes that came together. So each of these black holes was about 30 times the mass of the sun, incredibly massive. And when they came together, they produced that very strong gravitational wave signal. Now, this system is actually very similar to two neutron stars coming together, but one of the key differences is black holes, they have no light. And so you can think up some crazy theories for why you might be able to see this merger in light. But it's because no light escapes from a black hole, it's actually very hard to think of something that's reasonable for that scenario. Neutron stars, on the other hand, because you can see neutron stars to begin with, when they collide, there's at least a hope that you would see some light along with it. Now, getting back to the signal here, this is the actual data. This was what was measured. And we can make the comparison to what Einstein predicted. And it's hard to see because as I put the prediction on, it's a smooth line on both plots. It's hard to see because it's so good, is that the prediction matches the data almost perfectly. And once again, Einstein is right. It gets kind of boring. And so this was an astounding discovery, because for millennia, we've been looking at the universe through light, through photons. And we finally get the ability to look at the universe in another way through gravitational waves. And that's like somebody going through life and all of a sudden gaining their sight. It's just a completely new way to look at the universe. And this discovery, resulted in a lot of fanfare and press, and also the 2017 Nobel Prize for Physics, which went to the people who set up the experiment and really ran the thing for decades against all the headwinds that came along with it. It's just a fantastic thing. Now, one of the interesting things, if we go back, this is actually exactly what you see. This is much more complicated, where you have time on the bottom here again, you have frequency on the top, and then the strength of the color here tells you how loud something is. And if you notice, these frequencies are not too different from what an audible frequency that you can hear with your ear is. And so people get cute and they make really what this sounds like. So you can listen to it, okay? And we'll listen to it at its real level here. Okay, we did it twice. That's what it is. Now that was a little hard because these are black holes. The frequency is kind of low. It's not that exciting. So we can increase it like an octave and maybe 2 octaves. And that's what you get. So maybe we'll do that one more time just to. So that whoop, we call that a chirp. And so that's the signal that we're really looking for, is that chirp. All right, now, getting back to neutron stars. As I said already, neutron stars are this great gravitational wave source. They're also incredibly dense. They can come together and have these massive stars be moving at maybe a third the speed of light when they finally merge. But they have this huge advantage over black holes, and that's that they actually have some mass. And so we've simulated what happens when two black holes come together. So this is a simulation. And these black holes, as they come together, you can see up in the upper right, this is in milliseconds already. When they come together, they shear, and their gravity will pull the two neutron stars into one, which will probably eventually become a black hole. But importantly, because of conservation of angular momentum, there's a lot of material that's coming out in these what we call tidal tails that's unbound from what this neutron star or black hole would be. And that material gets out forever. And it has this great additional piece of it. And usually you don't like this, but in this case we love it. It's radioactive. And that means that it's got its own power source. And as that material decays away, it heats up that material and it shines. So there's light. Okay, so now a little more than a year ago, August of last year, I was in Copenhagen at the Niels Bohr Institute working for the Kavli summer program, which was specifically on gravitational waves. It was a month-long event where it was fantastic. I got to work with students, interact with other people. It was great. And we got to talk about gravitational waves. And I gave this great lecture, actually, towards the end about how difficult it was to see light from these neutron star mergers. At the time, my two graduate students were there with me. So on the left, Dave Coulter over here, and then on the right, Matt Siebert. They were there as well. And after being there for 4 weeks, on almost the exact last day, I'd been there for so long, and with my partner, and I'd just been working nonstop. And I said, I'm going to take a half a day off and just make it so that my partner doesn't leave me. And we went to this place called Tivoli. So if you've been to Copenhagen, you probably know Tivoli. It's this old amusement park right in the center of town. It was the inspiration actually for Disneyland. Walt Disney went there and saw rides like this on the left, and he was like, oh, I can do that in California. And I particularly liked this ride, the astronomy ride, where you go around in these little spaceships. And so I just took the afternoon off, not even the whole day off. And while I was in line for the carousel, this exact carousel, I looked at my phone. The line was a little long. I looked at my phone and saw this message from Dave. So Dave said at the top here, "Stop what you're doing and check your email." And so it actually took me a little while for me to look at my phone. And then what I said was, I don't have email now because I was traveling internationally. I was too cheap to actually get the data plan. So I say, all right, what's up? And then I'll walk you through this. Dave says, neutron star merger at a false alarm rate of 1 in 10,000 years. So exactly what we'd been thinking we wanted, at such a high false alarm rate that it had to be real. And then he said, coincident neutrinos and GRB. GRB stands for a gamma ray burst. This is the incredibly high energy photons. And so my first reaction to Dave is just position. I want to point a telescope at this, right? My second reaction is, this sounds like a joke. Why does it sound like a joke? Because he was there. He knew I was taking the afternoon off, and I thought, those Santa Cruz students, he's trying to ruin my afternoon. So we go back and forth a little bit. He makes a few mistakes on the coordinate conversions and things like that, which give me less confidence in all this. And so it comes down to this where I say, I might leave. But if you're joking and don't tell me now, I will not be amused. And neither would my partner. She would have been incredibly upset if I left and then, she had to be at the park by herself. And then, I'm still not completely convinced. And eventually Dave just, he finally is like, I'm not joking. I wouldn't joke about it. and that convinced me that I should probably leave. But by the time we got to the end here, I was at the front of the line for the carousel. So might as well ride the carousel. So this is me and my partner, and she of course is always fantastic, and me on the other hand, I'm obviously thinking about other things right now. Okay, so what actually happened at that time? Down here. We'll show LIGO and what it heard. And then up here is a satellite, this Fermi satellite, which can detect these gamma rays, these incredibly energetic photons. And so here's what, this characteristic chirp. That's what LIGO heard. And that's the sound of a GRB, a gamma ray burst. That's what Fermi heard. 1.7 seconds later, it detected a flash of light. Now, at the time, we didn't know if they were necessarily exactly coming from the same thing, because there are these gamma ray bursts happening all the time, and so it wasn't clear that they were necessarily associated. But we were pretty convinced early on that the gravitational wave source was real. So we got into action. So at the time, I was in Copenhagen, the star up here at the top, with my students Dave and Matt, and then in Santa Cruz, where my other student Cesar Rojas Bravo, and then my postdoc Charlie Kilpatrick, they were ready to get the data that we were going to get, and we were getting data from a telescope in Chile, and so in Chile. Our observer for one of the telescopes was Natalie, and then we have two collaborators from the Carnegie observatories who were also on telescopes, Josh on the left, Ben on the right. And so they are down in Chile. And so we had this global effort where we were getting data in Chile and then shipping it up immediately to Santa Cruz, where they were being analyzed. And rather than shipping it again across another ocean, we were just communicating very closely over those few hours. So down in Chile, we were using telescopes at Las Campanas Observatory, which is run by the Carnegie observatories. And you can see these amazing telescopes up here, the Magellan telescopes. They're 6.5 meter diameter mirrors, right? So 6.5 meters, that's about a 2-story building for a mirror that you can just move around anywhere on the sky. And there are 2 of them. That's where Ben and Josh were, but we were primarily actually focused on another little telescope on this mountain. That guy, called the Swope telescope. The Swope telescope, near and dear to my heart, is a 1 meter telescope. So its mirror is only 1 meter in diameter. It's actually something that you can give a hug to. And it's really a fantastic little machine. It's got a huge history going back decades. Now, we were using these telescopes to look for this light. But we weren't the only ones, of course. Everybody was trying to do this. And we were trying to do this with this tiny telescope. There are telescopes that have mirrors that are 10 meters in diameter. We use one called the Keck telescope all the time. So this is small potatoes compared to that. So really, this is us, trying to beat out these other teams. We're a small team. Some of these teams have almost 100 people working on them. We were just a handful of people. And just for one comparison, this is one of the field of view of a 4 meter telescope instrument. It covers about 3 square degrees of the sky. In comparison, the Swope instrument covers about 1/4 of a square degree, so significantly smaller. And it's also 4 meters in diameter, so it's significantly larger mirror, which if you combine those 2 pieces, just that we're looking at this tiny bit of what they can look at and that they're so much bigger, they get about 200 times the photons that we get in a given time. So that's really the David and Goliath there. But we had a strategy. We had a way to beat them. And that's noticing that the universe is clumpy, and so we should target the clumps. And so this is a picture of the sky where we're looking at slices in distance and pointing out every point is a galaxy on the sky. And what you can see is just like people live in cities, and those cities actually are kind of clustered together, what you see is that galaxies are the same way. That galaxies where all the stars are clustered together. And so rather than just looking at blank space where there aren't any galaxies, where there aren't any stars, where you wouldn't see necessarily neutron stars, we looked at the galaxies. So LIGO kind of tells you where to look. They give you a bullseye. This bullseye is 30 square degrees. That's about 120 times larger than the full moon. Okay, so it's roughly just saying, it's somewhere over there. And if you have a big telescope that can, look at large bits of the sky, you might just, mow the lawn, just pave over this entire region. But us, because we had this smaller telescope, and we decided to look at galaxies. So I'm going to walk you through. We had to wait several hours, in fact, from when LIGO detected something for the sun to set in Chile. When the sun was up, we couldn't do anything. So we had to wait. And then, of course, right after sunset, it's still pretty bright. You have to wait a bit. But we got our first images 46 minutes after sunset. And what I'm showing here is the galaxies that are in our first image. So our first image, we were able to find 3 galaxies. Okay. And I'm going to step through image by image, and the clock will go with it. And so, all right, our second image, a couple of galaxies, a couple more. Oh, that one had a whole lot. That was a nice cluster of galaxies. Keep going along. And then in our 9th image, we found something. So it only took about an hour after sunset. And, very quickly after we started observing to find something, our 9th image. And so one of the great things about this whole experience is that because we were on all these different continents, we needed to communicate, and we used Slack. I don't know if anybody here actually works for Slack. They've been very kind to us. So we use Slack to communicate, and so this is sort of carrying on from after those text messages. Dave at the beginning just says, I got Ryan on text, he's on his way, right? So as soon as I got the text messages, and I rode the carousel, then I rode my bike back to my apartment, got my computer, then went to the university. In the meantime, everybody else is trying to figure things out. Eventually, I'm here, I'm like, all right, I'm at my apartment, and we move through this. And we have a few hours before the sun sets, so we're preparing. And we're doing all sorts of things, checking over our algorithm, making sure that everything's right, swapping coordinates to make things more efficient, all this stuff, until eventually we're taking data. And Charlie, the guy all the way on the left from the first picture, he started looking at data. It's being shipped up. And so I asked, once we start getting the data, do we see galaxies? We should see some galaxies. Did we not screw up? Are we just pointing at blank sky because I was messing with the coordinates? And Charlie says, yep, there are 4 galaxies in our first image, or one of these images. Great. And then he says nothing in the next field, and I get a little worried, but I'm like, no transients, right? So that means something like a supernova or something else that wasn't there before. And he says, no transients, image is fine. All right, fantastic. We're not expecting to see many. There just aren't that many supernovae. There aren't that many things that are going bump in the night. So we really weren't expecting to see much. We keep going on for a little while, but not too much longer. We get to this, and this is going back to the very beginning of the talk, where Charlie says to me, found something. It's probably like the most nonchalant way of saying it. And, honestly, my reaction is not that much better because, my reaction is just, wow. And then Dave just responds with an exclamation point. But this is the moment. This is the moment where everything that we had built up came together and we were able to find the light. And so what did Charlie actually see? So first he shows us an image of a galaxy in the center here. In the center of this green circle is a galaxy, taken more than a year before the gravitational wave source. So it's just a galaxy. It shouldn't have any supernovae or anything in it. All right, so orient your eyes, and I'll flip to our new image. So this is our new image. All right, and my answer at the bottom here is yep. So of course, I'm a trained astronomer. I look at these things all the time, and to me, what's on this image was like a thumb in my eye. It was so obviously there. But for you, I'll give you another shot. All right, so here again is the before. Let's see the after. Everybody get it? All right. Why don't we zoom in? This is the discovery image. And so if you already saw it, you maybe already know. But this is what we do for the undergrads to start them off. We make it easy for them. And so can you find it now? So that is what we call the electromagnetic counterpart, the light that corresponds to this gravitational wave event, this neutron star merger. And this is the first image of that light. That Fermi saw something, but it can't make images just because of the way their technology is. But we can make images, and this is the first one. This is already being published in textbooks. This is, we like to say it's what started a new field, a new scientific field. And it just so happened that the Hubble Space Telescope imaged the same galaxy only a few months earlier. And it's a little bit hard because the Hubble data are so good and so crisp. But you can see at the point of the arrow, there's nothing there in the Hubble image just a few months earlier. And there's something there in our image. So our first images were taken about 11 or 12 hours after the LIGO detection. And this is what we saw. This is a color image that we were able to make because we got multiple wavelengths for the light. And then we continued to follow this for several days. And so just 4.5 days later, that's what it looked like. It had faded dramatically and became very red. And that is not like a normal supernova. That is specific to a neutron star merger. And so what's really happening? So these two neutron stars are losing energy because of gravitational radiation. They are coming closer and closer together. LIGO picks up that signal. They merge. You have a gamma ray burst. You have this material that's ejected out that starts off blue and then over time turns red. And so this comes back and we say, all right, let's go all the way full circle. What was actually created? What made that blue to red transition? Why is it different from supernovae? And the answer is really the gold, or really heavy elements in general. And so simulations by our colleagues have shown that, where do you actually make the gold? So the gold spot is where you make the gold. So when you merge this, you see all this material that is coming out and is unbound from what ends up being a black hole. And you say, how much material is there? Well, Jupiter, it's about as massive as Jupiter. Way more than all the gold in our sun. In fact, it's about enough gold for 6 million suns. That's a lot of gold. So what we found actually was not just that it made gold, it made all sorts of heavy elements. It made all the elements that are heavier than iron. And so if you look at the periodic table in this particular way, where the elements came from, a lot of this diagram on the top here are just exploding stars, different kinds of supernovae, but the bottom half are neutron star mergers. That's where the gold, the platinum, tin, all those heaviest elements, where they came from were neutron star mergers. So here's the full team, including some people from other institutions. And again, I really just want to bring this back to the fact that this was a team effort run by these incredibly amazing colleagues of mine. And I just couldn't be prouder. And really, I think a tribute to what they were able to pull off is that this last year, this discovery was considered the 2017 Science Breakthrough of the Year across all sciences. So, I'm all the credit should go to all the young people. They did such amazing work. But if I can leave you with one lasting thought, it's that when you stare down at your wedding ring or think about your gold fillings, realize that came from a neutron star merger. That's neutron star debris. And so before when we said we're all made of star stuff, that was a very nice way to think about most of what we're made of. But we're not just made of the remnants of these normal stars. We're also made of these incredibly cataclysmic events. And that's part of our history as well. And so I'll just say thank you. We got funding from all sorts of agencies, but in particular, we got money directly from people giving money to UCSC through the Giving Day. We get money from NASA and the National Science Foundation, which means if you're a taxpayer, you gave me maybe about a half a cent. Thank you. But really, this is what we do for society, and thank you very much for supporting science generically. And of course, there are a bunch of private foundations who have also been incredibly supportive. We couldn't have done it without them. So thank you all. My email address is at the bottom if you have questions. We have time for a few questions now, and then eventually, we'll be able to mingle afterwards. So I believe there are microphones for questions. Thank you very much. So I think there's a mic right behind you.
Forgive me if I'm
No,
remembering-
just wait. All right, go.
Forgive me if I'm remembering incorrectly, but you said neutron stars are about the size of a city?
Yeah, approximately. So like the diameter might be 14 kilometers, and so it's roughly right, a little bit bigger than San Francisco.
How do you then combine two things that are roughly the size of a city and get as much gold as the size of Jupiter?
Oh, sorry. So it's not the size of Jupiter; it's the mass of Jupiter.
Ah, okay.
Yeah.
Sorry.
So it's actually put in a smaller area at the beginning, and then it's dispersed throughout our galaxy. Yeah. A lot of other questions. Anybody can, whoever's closest to the mic.
Thanks for a great talk. Congratulations.
Thanks. Yes.
Hey, how often would you say these neutrons?
Oh, sorry. There might be something with the mic.
You're John, right? Hey, thanks.
Okay.
Hey, okay. Thanks for great
Yeah.
talk and congratulations.
Thanks.
How often in a galaxy, Milky Way-sized galaxy, does a neutron star merger happen? And hey, while you're at it, tell us about black hole mergers.
Yeah.
also.
Great.
Thanks.
Great. So, so both are incredibly rare, and unfortunately, there's only one neutron star merger that we have right now. So it's hard to figure out how often they occur. But we can make some estimates there, and so I think a good way to kind of set the stage is to say how often does a star explode in the Milky Way? That happens roughly every century. And a neutron star merger probably happens once every million years in the Milky Way. So they're rare for sure. And you'll have many more stars explode before neutron stars merge. And black hole mergers are even rarer.
Could you go back to?
Oh, sorry, wait for the mic, please.
Oh, I just wanted to ask if you could go back to that periodic table. I want to take a picture.
Sure. Yeah, no problem.
So back a few decades ago when I had my astronomy education, we were taught that all the heavier elements came from supernova remnants. Do we still believe that supernovas also generate those heavier elements, or do you believe that they are only generated by the neutron star collisions and they are not generated by supernova? And the last part of my question is, do we know if heavier elements are also created from black hole collisions?
Okay, great question. So first, we don't know definitively that these heavy elements are made from supernovae, but we think that they should because the recipe is essentially the same, where you need to have a lot of neutrons, which you get when you have a star collapse. The core collapses down to a neutron star, and there's the possibility of producing a bunch of neutrons because you have these other particles called neutrinos that fly out and can make some neutrons. So at least it's physically possible to do that way. So probably some fraction comes from that. What we can also say, though, is that we roughly know the rate of neutron star mergers, and we know how much of the heavy elements were made in that one neutron star merger. You can just multiply those together and figure out how much material is made every year. And that seems to be enough. Now, you can always say, well, we don't know the rate that well, and this one event may be atypical. And so there's still plenty of wiggle room where, massive stars collapsing down could produce a sizable fraction. But if we just take, things at face value, I'd say that it's a small fraction right now.
So the supernova remnant would be a very small fraction of those
For the heaviest elements.
Heaviest elements.
Yes.
They still can be created, but in much smaller quantities.
So in any given supernova explosion, we know that it has to be a relatively small amount, but there are a lot more, right? Like we said, there are a lot more supernovae. So when you just sum everything up, they still might be a sizable fraction, but I think if we take things at face value, they're probably below 10%.
And what about black hole collisions?
Yeah.
Do those create heavier elements?
So from everything that we know, it shouldn't. So when two black holes come together, nothing should get out. You can potentially have some material that's orbiting the black holes and things like that, and when they come together, that material can get flung out. But as far as I know, that really shouldn't produce heavy elements. So you might see some light, but I think the heavy elements are particularly difficult in that case.
Thanks.
You're not just looking at events in the Milky Way, right? You're looking at all known galaxies.
That's right.
Yeah.
Yeah. So yeah. In fact, we've never directly seen a neutron star merger anywhere except for this one galaxy that's about 120 million light years away.
Right.
Yeah.
How did they know that the first example of the gravitational waves was two black holes rather than neutron stars?
Great. Great question. So that wiggly line that we saw.
Yeah.
That can tell you a whole lot about the system. So how those like how strong those lines are, how quickly they come together, things like that tells you about the masses of the two things that come together. And so so from that you can just figure out a lot of things, like roughly how far away it is, roughly where it is on the sky, how massive the components are. It's even better the total mass when you add together. That's an easier thing to measure, and a few other things that are really interesting, like how they're spinning around and stuff like that. But it's all embedded in that data.
I see. And what are the wavelengths of the LIGO lasers?
Oh, that's good. It's in the infrared, but I'm not sure exactly what the wavelengths are.
6.4 microns.
All right. Thank you very much.
I can shout my question.
Well, here, why don't you wait for the...
So if I understand, the detectors that you had, the gravitational wave detector, was like a microphone listening, and then you had to find where to look. So if you were the first, how close was everybody else?
Yeah, good. So it is sort of like a more like your ears. So you can triangulate because you have two ears. You can triangulate sound. That's a more apt way of thinking of LIGO. In the same way, right? So there are some degeneracies. If when you get home, you can try closing your eyes and snapping your fingers in front of your head and then above your head, and you won't really be able to figure out where it is along that plane. But if you snap over here, you'll be able to say it's to your right. Now, in terms of the other people, all those Goliaths that were breathing down our neck, they were relatively quick. So within an hour, there were a couple of other teams that saw things, but we saw, not only did we see it first, we announced it first, and because we were so quick, those other guys who were using the Magellan telescopes, not only did they get a couple of images, but they have additional instrumentation, so they were able to switch to a mode where they can get a spectrum, which is like shining light through a prism. And we were the only ones in that first day to get a spectrum, and it was just the conditions were so that the object was near the horizon and setting, and so we only had a short period of time before it would set in Chile, and then you have to move over to the next telescope. And so because we were so fast, we were able to alert the other telescope, and they were able to get that data. And the other teams that were a little bit took a little bit longer to get that information. They didn't have time to do that. So it's, I don't want to emphasize so much the race to get there. It's good to be first, right? Right? Like, I'm not going to downplay that, but I think scientifically the more important things are those other things, that we had unique information because we were able to find it as early as we did. Sorry, why don't we wait for a mic just so everybody else can hear?
Science aside, how did it feel?
Oh, yeah. Yeah, so this is part of the story that I didn't tell is, so because I was in Copenhagen, even though the observations occurred in the first hour or so in Chile after sunset, in Europe that's nighttime, right? And then, of course, after we got the data, we still had to analyze things. We were setting up observations at other telescopes, So we were up for the entire night. And I got back to my apartment around 6:30 a.m. or so. I got back. I woke my partner up, and I told her, just like, we did it. And it was fantastic. And that feeling lasted for about the hour that I couldn't sleep, and then I got back to work, and so I didn't talk about this whole aspect, but that team that we had there, we just our team wrote 7 scientific articles in 2 months' time. 4 of them went to this journal Science, which that's a decent amount of work. And so for those 2 months we weren't sleeping much at all. And at the time the whole news was embargoed, so we couldn't really talk to anybody. Like our other colleagues, my people down the hall from me, I couldn't tell them about this until we had a press conference 2 months later. So it's a very interesting thing where yes, you're very excited and it's just incredible, and you learn so much about the universe in one go, but at the same time, everything's incredibly hectic and you're under the gun, and at the same time, you can't tell anybody why you're not sleeping. Yeah.
Just a quick question. You mentioned that the gravitational detection was made about maybe 1.5 seconds before the gamma ray burst.
Mm-hmm.
If they both travel at the speed of light, I'm just wondering, why wasn't it simultaneous?
Oh, this is a fantastic question, right? So first of all, just the fact that they were separated by only a couple of seconds already tells you that gravitational waves travel at essentially the speed of light. They moved over 120 million light years at so similar in speed that they had to have gotten there to roughly 2 seconds. All right. So first of all, but why the 2 seconds? Well, so just because you had this merger, that doesn't mean that the photons started traveling at exactly that time. So what we think actually happened was you had this merger, and the light was trying to get out, but it couldn't quite get out yet. And so it just took a little time for the photons that were generated in the merger to actually get to the surface where they could just free stream. So they were just rattling around inside for about 2 seconds, and then eventually they got out. Diffusing out, exactly. Yeah. All right, so I think we have time for one more question. We have one hand up. So if the mic can get over to you.
Did you say earlier that there was also detection of neutrinos?
So this is great. So Dave said that. So Dave put in his text that there was a detection of neutrinos. And so initially there was a report of a neutrino detection that occurred at roughly the same time. And so people put that out there. It turned out after not that long, just a few hours, that they realized that neutrino detection was not coming from the same part of the sky. So it was unrelated. But for a little time, there was the possibility that we saw this event in 3 different forms of what we call messengers. So photons, gravitational waves, and neutrinos, which would have been fantastic. And we're waiting for the next one where we actually get that. But for this one, it turned out that we didn't see any neutrinos. Okay, so thank you very much. I think we'll all mingle over here. There's probably still some wine left. So I'll see you over there. Thank you very much.